Then today we're gonna just do a quick review of that, and also we will go and do mesh analysis. Right, we did branch scoring analysis. Now we're going to do mesh analysis, which have two approach. And after we do that, then we will do an example. Basically, there is three different methods that we're going to do, but we're gonna explain all three up to when we get the equations, and then we're gonna do only one example to solve the equations, because all three methods lead you to find the system of linear equations, and then you have to just solve the system of linear equations. So we have to only do one example, because all three methods lead you to the equations only, and then we do one example to solve it, and then we move on. Okay, so hopefully you followed my advice from last time, which was to review how to solve system of linear equations, which I just remind you again was using Cramer's theorem or Cramer's law or determinant, right? All the same method, different. They may call it different in different books, right? And I mentioned that when you learn this in math, right, you learn it for doing substitution, you then by doing elimination, and you learn it by solving it using determinant, which is Cramer's theorem, right? So this is what we're going to be doing today. And also we will do Thevenin theorem and maximum power transfer. Okay? Okay. Let me just, I will, give me 1 second because I have to log off and log on in a different computer. Okay, can you hear me here? Okay. Let's walk to what we left off last week. We're going to review up to what we left off. So being review, we're just going to go through it quickly so you can kind of remember last thing we saw. I think we didn't finish chapter 8. That was chapter 8, right? Okay. So with the source conversion, last time we used to convert a practical voltage source into a practical current source. And we explained the procedure to it and was basically using Ohm's law, right? You see what we did. For example, just to remember, we did the last week was if we will convert from a voltage source into a current source, right? As we see here, we just use Ohm's law to calculate the current, which is I is equal to E over RS, and this is RS, and then we get the current, and the current will point the direction when you have the positive sign here. And then RS is just the same as RP and put it in parallel with the current source, right? So this is how we mentioned that we convert a practical voltage source into a current source, right? Also, we mentioned to do the opposite, right? To do a current source into a voltage source. And again, we use Ohm's law in order to calculate E. We just take the value of I and we multiply by RP, voltage. Voltage is equal to I times R. So we get the voltage, and then RP is equal to RS in series, and this is the conversion. Basically, this source here is equivalent to this source, and vice versa, right? So we did an example how to do it, and then we showed that IL was the same in both cases. We did have to how you call this, simplify circuits when you have sources in parallel, right? Current sources in parallel. We mentioned you cannot place two current sources in series, right? And we start here when we do the branch current analysis. We develop the equations. We explained what a independent loop was, what a dependent loop was, what is a node, right? And we did a procedure in how to develop the equations, right? So this is where we left off, right? So let's just go really quickly, just for you to remind how to get the voltage, the equations for this circuit that's here, right? It's easy, right? So first of all, you assign a, let's just delete this one here because I don't want to confuse. So this is the circuit. Remember, we did this last class. We did the whole thing. We explained how. We're just going to quickly review it so we are on the same page. So what we do first, I mentioned, we assign a current to each branch right? After we do that, we assign a voltage drop across this resistor. In this case, this is plus, minus, and plus, minus, because always the current go into the higher potential, and we explain why already. So this is going to call V1, this will be V2, and this will be V3, right? And we know that V1 is equal to what? V1 is equal to I1 times R1 if we apply Ohm's law, right? V2 is equal to what? Is equal to I2 times R2. And V3 is equal to I3 times R3. So the procedure to do this, we're going to go around the loop. For example, we're going to start here. We're going to go around the loop. And we're going to be adding all the voltage around the loop. We're going to go here. We go around this loop here. And we're going to be adding all this voltage around this loop, right? And also when we go around the loop, if we go across an element and then we go from a lower potential to a higher potential, we're going to call this a voltage rise. We're going to call it positive. Just for your information, you can call it whatever you want. You can call it positive or negative as long as you keep the same idea through the whole circuit. You will find some book that how they do it is, if when they go, they encounter a negative first, they call it negative. Then when they go, if they encounter a positive, then they call it positive, right? You can use any way you want, but you have to stick to the same thing through the circuit, right? For me, I think it's more intuitive for the inexperienced students to learn it this way from low to high, positive, because a voltage rise and a voltage drop negative. So it kind of intuitively you can remember to use it through the whole circuit. But you can use whatever you want as long as you use the same concept through the whole circuit. Okay. So when we go, let's go to loop one. So loop one, we say that this is going to be E1 minus B1, but B1 is equal to I1 times R1 minus V2, but V2 is equal to I2 times R2 equal to 0. Now let's rearrange this. This is equal to I1 times R1 minus I2 times R2 equal to E1. And that will be my equation number 1, right? This is my equation number 1, right? So now we will go through the second equation, right? We go to the second equation. Then this is going to be E2 minus V3, which is equal to I3 times R3 minus I2 times R2 equal to 0. So that's going to be equal to I2 times R2 minus plus, I'm sorry, I3 times I3 equal to E2. And that's my equation number 2. Remember, here you have 3 unknowns. You have I1, I2, I3, but you have 2 equations. So you need a last equation. And we say last time that if you put a node here, oh, you don't put a node, you just mark this node here, and then you apply Kirchhoff current law. We said that all current leaving the node must leave the node. So in this case, I1 plus I3 is equal to I2. Right? Now, if I substitute any of those 3 current, I solve for any of those 3 current, I substitute in those equations, now you're going to have 2 equations with 2 known. You can solve these, right? So remember, R1, R2, R3 are just given values which you will have in the circuit. And E1, E2 most likely will be given 2. So this is what we did last class, right? Any questions so far on this? What we did last class? We leveled up to this point, I think it was. Any question you have on how to get a system or linear equation from the circuit here? Okay, I assume it's okay then. Now, we will do now mesh analysis, where you have 2 approaches, right? Remember, in the other circuit, we have the same type of difficulty for the circuit, the same type of circuit, right? Kind of the same type of circuit. E1, R1, R2, R3, whatever, right? And we have 3 equations. That's why I said we want to do an example. We won't do an example for each one of them because all 3 lead to the system linear equations. We're going to do all 3, get the system linear equation. After that, we do one example just to solve the equations, and that's it. Because it's the same thing for all 3 at the end. Just math, right? So let's say we have the circuit here, right? We have the circuit, and we need to analyze it. Now, you can use branch current analysis, which is the same one that we just did, or you can use what is called mesh analysis, the general approach, right? So in order to do mesh analysis, the general approach, you have to do almost the same method. The only thing with this method you're going to have is here will be 2 unknowns because you have only I1, I2, so you have to mark 2 loop currents in here. That's the only thing. You have to mark 2 loop currents and you will have your equations. After you do that, so we will discuss or we will go through what is the process in order to get those equations, right? We're going to go step by step and we're going to show you how to get these equations one by one, right? Okay. So if you want, you can take down and you can, I mean, you should take some notes. So the way to do this, we're just going again to assign two loop currents into the circuit. We will go around this loop, adding all these currents, right? So we're gonna go like this. Let's do one. First, let's do this. For purpose of this explanation, you can assign the loop current any direction that you want. Doesn't matter. You can do clockwise, you can do counterclockwise. It doesn't matter. As long as you assign the correct polarity to the voltage across, right? For example, here we will go and we will assign two loop currents. So we're going to assign it, all the current will be clockwise. When I personally do an exercise, I don't have a specific direction. I take a educated guess what is the best direction to place the current, depending on the polarity of the voltage source and the amplitude of the voltage source itself. Because I want to get as much positive current as I can, just to get the positive current, that meaning that the direction I choose is the correct one. That's it, not because of any other reason. So just for a way of consistency, let's use all of them being clockwise, but you can use anything, right? Just for today's explanation. So we're going to do the circuit, and we assign the two current to be in the clockwise direction, right? Like this, like that, right? Right, so that will be the direction I1 and I2. After we do that, we will assign the polarity to each voltage drop across each element. This E1 is given to you. You don't have to assign. E2 is given to you. You don't have to assign. Here you have to assign. So since we select a clockwise direction, so the current will go here in this resistor one from the bottom to the top. Always when it comes in is a positive, leaving negative. So it goes here, positive, leaving negative, right? And then this is given to you, this is given to you. Now we go to I2. I2 we also going to go clockwise. But look at this. Now R2 is positive here and negative here, opposite from this side. Because the polarity that you represent here is due to this current. And the polarity that you represent here is due to this current. Right? So let's go and write our equations. This is the general approach. I repeat again. Right? So I write this. So I will start writing my equation from point A, right here. I will go around the loop for example, from point B around the loop like this. And we'll come to this way. And the other one, I will go this way also, right? So I will follow also the direction of the current in the way that I'm going, but I don't have to. You can go any direction, right? So I'm going to do is going to be from minus to plus is going to be E1. E1 minus I1 times R1. Now minus a current times R2. what is the current? So look at this. In this case here, you see that I1 is going down this way. And I2 is going up this way. So they are going opposite direction. So that means if they're going opposite direction, they have opposite sign on each other. Which one is a positive for you? Well, I'm using the polarity negative because I'm going from top to bottom. That means that the one that's going positive to me will be I1 right now, because I1 is my reference for this case. So it's going to be I1 minus I2, right? I1 minus I2. Now minus E2 equal to 0. Why minus E2? Because I'm going from positive to negative. That's why it's minus. So I will rearrange this, right? So if I rearrange this, it will be that I'm going to have I1 times R1 minus I1 minus I2 times R2 equal to E1 minus E2. Right? Now I will substitute all these numbers, right? I1, I don't know what it is. It's unknown. I1 times R1. R1 is 1, so it's going to be just I1, right? I1 minus I1 times R2. R2 is equal to 6, going to be minus 2. I'm sorry, minus 6. Minus 6. I1. Now minus time minus is plus. Right? It's going to be plus 6I2 minus equal, I'm sorry, to E1, which is 5, minus 10, which is minus 5. And that will be my equation number 1 for my general approach, right? This is the general. I would write it later, but this is the general approach. Let's do now I2, right? Which is this one here. Right? So I2, I go the same thing. I go into a star at B. I will go this way, and end at B again. And let's see what I get. So this is going to be E2 minus a current times what? R2. But again, in here, you see that I2 is going up and I1 is going down. I'm doing this one now. And I took this voltage as a reference because I put this negative here. Because I'm going from minus to plus. What direction made this plus and minus? This one here. So what it means is I2 is my reference now. So then it's going to be I2 minus I1. Right? And then I continue to minus I2 times R 3. Equal to 0. Now let's rearrange this, right? So if I rearrange this, it's going to be minus I2 minus I1 times R2 minus I2 times R3 and so I can convert this to positive if I leave the other sign. So this is all positive here. Equal to E2. Right? Now let's substitute this. So I2 times R1. I'm sorry, R2. So it's going to be 6 times I2 minus I1 times R2, which is equal again to 6 times I1. Right? Then plus I2 times R3, which is 2 I2 equal to 10. Right? Now this is going to be my equation number 2. So let's rewrite this equation in a more simpler way. So let's rewrite this. I'm going to write equation number 1. I will take common factor for I1, right? So you see I1 in the first one is I1 minus I6. There's going to be what? Then it's going to be minus 5. I1. I'm sorry, guys. I made a mistake. Look, equation number 1, I made a mistake. Why show you the mistake now? Look, you know when we're doing this here? Since I separate both of them and I kept E1 the same sign, E2 the same sign, I have to change the sign for this one here. I realized something because I1 shouldn't be 5. So what I mean, you see I change I1, I put a positive here. Then this should be positive number, right? So that should have been positive here. We will rearrange everything for me. Now if that's positive, this is positive because it's I1 times R2. And then this is negative. This is negative. Does that make sense what I say? Everybody understand what I did? You understand what I did? Oh, no? Okay. Simple math. I have this equation here. E1 minus I1 times R1 minus I1 minus I2 times R2 equal to E2. Minus E2 equal to 0. Everybody understand this part here? Okay, so from here to here, what I did, I separate my independent variables. So I will talk about very math terminology so you remember what it is. In a independent variable for my dependent variables. What is my dependent variables? Whatever depend on I. My independent is just the constants, which is 5 and 10. You see? So since I separate both of them, okay, I keep E1 minus E2. So I need to keep those two. Now I need to subtract by the opposite of this. The opposite of this, so this eliminate here. And stay in the other side of the equation to keep the equation in equilibrium. I just explaining math here. This is just math, not circuits. So when I did here, if you see I1 times R1 here, right? It's positive. You see that? Now minus I1 minus I2 times R2. Then this should be positive here. That was a mistake. So everybody's okay up to when I got this one here. So now I will rearrange. I'm simplifying this equation. That's the only thing I'm doing right now. Right? So it's going to be here I1 plus 6 I1. So it's going to be 7 I1. 7 I1, right? Now 7 I1 minus I2 times 6, right? Equal to minus 5. So this is my equation number 1. The first one. I just rearranged it, right? So let's do my equation number 2. Again, I see here minus 6. I put it on red, so you follow the same convention. So minus 6 times I1. And then I see I2 is 6 plus 2 is equal to 8 times I2 equal to 10. And this is my equation number 2. And that's it. After this is just to solve I1 and I2 using the method that you learn. So do you see the difference for the same type of circuit? When you use the branch current analysis, you have 3 equations. Now, for the mesh analysis general approach, you have 2 equations only. You see how it's becoming easier. And this is called general approach, right? Any question into this one here? So we have the 2 equations. We will explain in a little bit how to solve it. I hope you know anyway. But we will explain it just in case. But you should know. Any question up to this point here before we move to do the mesh analysis format approach, which is a very simple, straightforward. Any question, guys? Are you okay up to here? If I give you the circuit, can you get those 2 equations here? Okay, no question. Now, my 2 equations are these. These are 2 equations I need to solve, remember. I need to solve this one. I need to solve this one, right? That's what it is. Let's do now the format approach, right? Format in this side. Format approach, right? So to the format approach, it's the same thing. Step number 1, right? The step they're going to apply is the same thing for general approach and general format approach. It's the same steps. You get your circuit, you assign the 2 loop currents, as we did. In this case, we assign it clockwise for whatever reason, right? Then we assign it this way. When I say for whatever reason, because it's just arbitrary, whatever reason you want. whatever direction you want, right? So, and then this also is clockwise. After I do that, I will assign my voltage, right? But you don't really need it for this approach, right? So you assign those two, and then you're gonna do a serious step. So what you're gonna do first to do your equation number one, which is going to be in blue, equation number one, you will add all the resistance which current one goes through. You add them up and then you multiply by current one. Right? Let's do that. So let's draw all the resistance. So it's going to be R1 plus R2 is going to be 7 because it's 1 plus 6 is 7. 7 times I1. Then we're going to take all the resistors and add it up that are common to I1 and I2. In this case is R2. R2 is common to I1 and I2. So we're going to get the resistor. We're going to add it up. In this case, just one, so it's just one. You don't have to add it to anything else. And then we're going to put a minus sign. And then we're going to call this 6I2. Right? And then we just call equal. And we add all the voltages. Since we're going clockwise, right? Clockwise, it's going to be E1 minus E2, which in this case is minus 5. So do you see in one step, you got this equation here. Any question? You see how the two methods are the same, but one you have to go step by step by step. In one method, the format approach, you go directly in one step. I usually use that one, the second one. It's easy. There is less chances to make mistakes. Actually, when analyzing a circuit, not even for the class, for anything else, I use that method. It's straightforward. But everything comes from the branch current analysis, the one that we explained first. Even mesh analysis, general approach comes from that too. It's the same thing. So now let's go to loop number 2. Okay, loop number 2. Loop number 2. Let's do the same thing again. We will go around the loop, right? And we will add all the resistors that current through goes through. In this case is R2 and R3. In this case is 6 plus 2 is going to be 8. So it's going to be 8 times I2. Then we're going to subtract we're going to add all the voltage, we're going to subtract we're going to add all the resistors that are common for I1 and I2. In this case, just one, which is minus 6, and we're going to multiply by that current, which is neighboring to us, I1 in this case. And then we go around the loop and we add the voltage. In this case, is E2 equal to 10. And that's it. I have my second equation in one step. You see that this is equal to that, and this is equal to that. But to get this, I have to go through all these steps here. Any questions so far here? Any question? Do you have any question on how to get the equations using branch current analysis, using mesh analysis general approach, or using mesh analysis format approach? Can you go to the second loop? Okay. The second loop is like this. So we're going to go the second loop. Second loop, we going to get our reference, everything is I2 right now because we're in the second loop. So we will add all the resistors that current 2 goes through. and that will be positive. In this case will be I1, I mean R2, and that will be R3, right? So R2 plus R3 is equal to 6 plus 2, which is 8. And we have that, right? Now, we're going to get all the resistors and add them up that are that two currents go through it. In this case, I1 go through here and I2 go through here, but they go in opposite directions. They go in opposite, so I have to call it negative because they go opposite direction. That's a thing that I failed to mention before. If they go on if they were in the same direction, they both going down or both going up, then this is plus here. It's negative because they both go in opposite direction. And it's negative because the other I2 is my reference, so going up is positive to me in this case, meaning that if going down is negative, that's why I have the negative here. So minus R2, which is 6 I2, and then equal, I add all the voltage source in the same direction I go of the current. So this is from plus to minus, from minus to plus is positive, that's why it's positive, and that's it. Did I answer your question about going over equation number 2? Any question? You have question, you don't have question? Let me see. Can you go? Okay, when the yes, but we will not be using I3 as we are trying to solve for that. In this case, there is no I3. Because we are only looking for I1 and I2. There is an actual third current here, but you can easily find it. The third current is the actual, the net current going through here. The net current going through, give me 1 second, here, which is the subtraction of I1 and I2, because they're going opposite way. If they were the same way, just add it up. But you don't need to solve, this is easy to get. So you want only two loop current to simplify to solve the circuit. Because you don't want to go from three unknowns, because to do the terminal with 3 unknowns is way more work than do the terminal with 2 unknowns, because you're going to have a 2x2 matrix. But if you have 3 unknown, then you're going to have a 3x3 matrix, which is a little bit more work to solve and easier to make or more room to make mistakes. Unless you have a 2x2. 2x2 means 2 columns, 2 rows. If it's 3x3, it means 3 columns, 3 rows, right? Any question up to this point? We won't touch this anymore. We're just gonna do an example, and then we'll go to AC. In AC, since I explained the theory here, I just go directly to solve the problem. But that's gonna be a few weeks from now anyway. When we do AC circuits, we're gonna use all this. We're gonna be using complex number. That's why I said to practice using Cramer's theorem, because to solve CET linear equation with complex number, one of the more or the easier method to do will be Cramer's. Any question up to this point here? Is everybody on the same page on this? This will be on exam number 1, by the way. Any question? I guess not then. Okay, so the circuit could be any different shape. So you can be this shape, it can be anything, right? This is just a different example. You can have 3 loops here, right? You can have 4 loops, it's all the same. All is the same, right? The only thing this here, you are going to have, look how powerful is this method. If you use branch current analysis if you were used for this circuit, look how it is now. Forget about this current down here. I'm gonna write the current on red, so you see the power of it. If you compare to the branch current, you're going to have one current here, right? Let's call this I3. Why this is small? Okay. I3. Now you will have a current here. Let's call this I2. You have a current here. Let's call this I1, right? You're going to have a current here. Let's call this I2, 3, I4. You're going to have a current here. Let's call this I5. And you're going to have a current here. That will be I6. Can you imagine solving a system of 6 unknowns? There's going to be 6 equations, 6 unknowns. That's going to be a very long. Right? Instead of you apply 3 loop currents and you can have now from 6 to 3. Way less than half of difficulty. That's why mesh analysis is a very powerful method. You understand the difference from the method 1 that we did? Method 1 that we did was only 2 loops. That's why we have 3 currents. But this is 3 loops, and now we have 6 currents. And then if we have 9 loops, you're going to have a big number of currents. So view mesh analysis is very powerful because you reduce the complexity of your problem a lot. Okay, let's do one example. And then we take a break after we do this example. And then after that, we're going to go to mesh. And sorry, to Thevenin theorem, maximum power transfer. And I think we will finish the day with that. I'm going slow. So you're gonna, if you see the syllables, we are falling behind because if I go at the speed that we're supposed to go here, we will have a little bit of a problem because remember, this is a review. I'm supposed to go fast in this because this is just a review. You're supposed to know all these from circuits 1 and from electronics. But for some reason, you forgot about it or something. So that's why I'm taking the time. That's why they put in the program, they put only 1 day to do this. We have to take kind of day and a half, 2 days, because I have to go very slow. But we catch up. Later on, we catch up. So this is when I told you that I need feedback because I don't know. I think I'm going at a good pace here because I have a couple of questions already. I'm not even sure if all of you are really, hopefully all of you are getting this. Let's do mesh analysis. And we're going to use right off the most straightforward method. We will be the mesh analysis format approach. That's what we're going to be using. If you want to use the mesh analysis general approach, you're welcome to. If you are use the branch code analysis, you're welcome to. At the end of the day, we're just going to get to the equations and then we solve it. So whatever method you want to get to the equations, fine with me. I don't have a problem with it. Right? So let's do this, right? Let's write here. Let's assign my loop number 1. And I'm going to call it that will be, oh, this is too thick. Let me put it smaller. Yeah. So we're going to assign this is I1 loop current, right? And then we're going to assign this to be I2. I2, right? For this method, you don't need to assign the polarities if you don't want, but remember, You could do that if you choose to, right? But this is given. The big bar, that's a positive, that's a negative. So that you have to, that's a given. Negative, positive, right? Now what are you going to do? Let's do loop one, current one, right? I'm gonna add all the resistors that I1 goes through. I'm gonna do two steps so you can remember, right? So it's going to be R1 plus R2 times I2 minus the resistor that is being that two current go through. In this case is R2 times I2 because I1, I2 they go in opposite direction through R2. That's what happened. Equal to E1. Now let's substitute these numbers, right? I could have done this in one step, right? I just added directly, but I'm gonna do it little by little so you can see. So this is equal to 1.2k plus 8.2k times I2, I1, I'm sorry. This is 1. I1 minus 8.2k times I2 equal to 9 volts, right? Now this is going to be 1.2 to 8.2. That's going to be 9.4. It's going to be 9.4k, which is 9.4 times 10 to the 3, right? K times I1 minus 8.2k times I2 equal to 9. And that's my equation number 1. Let's do my equation number 2. Question number 2 is I'm going to add up all the current that I2 goes through. In this case, R2 plus R4 times I2, right? Now minus R2 times I1, just because they go both in opposite direction, right? So this is going to be 8.2k times I1 plus 8.2k plus 1.1k times I2. I'm sorry. This is also equal to 6, right? Equal to 6 because of E2. And this is minus here, right? Minus 8.2k times I1 plus 9.3k times I2 equal to 6. And that's my equation number 2. So I have my two equations. That's it. After that is math. So to do that, let's do our determinants, right? That's what we said we're going to do. So you see I1 have a column in here. I1 have a column. And then I2 have a column, right? This column, this column. So I'm going to build a metric system for it. So let's call this one the determinant. Let's do different color. Let's do it black color here. The determinant of the system will be equal to the column of I1. It's going to be 9.4k, right? And minus 8.2k. Minus 8.2k, right? Now the column Y2 will be minus A 8.2K and plus 9.2K. That you're gonna get determined in a little bit of that. Then I will do the determinant for I1. So what I'm going to do is I will take the determinant of the system, right? Minus 8.2K, 9.2K. And in the column for I1, I will substitute it by the independent variables, which is this column here, 9 and 6. So this is going to be 9 and 6. And I have my determinant number 2. Now I need to get the determinant of I2. Which is equal to, again, the determinant of the system, or the first one on the top here, ds, 9.4K minus 8.2K. And then for I2, I will substitute by the independent variable, which is 9 and 6. And then I get that. So let's do the determinant first of ds. The determinant of ds will be equal to cross multiplication. So it's going to be 2. So I'm just going to put this to remind you a little bit how it is, but it's type of like this. This guy times this guy, right? And then minus this guy times this guy, right? This is just math, right? I put this so you remember. So basically, will be 9.4K times 9.2K, right? So it's going to be 9.4K times 9.2K minus so minus times minus, which is minus 8.2 minus 8.2 is pos, right? It's positive, right? So it's going to be minus now 8.2K or 8.2K squared, basically. 8.2K times 8.2K, right? That will be equal to 19 to 19.4K, right? Now the I will be equal to 9 times 9.2K minus 6 times minus 8.2K. This is going to be 132K, right? And then IS, this is 1, DI2 is equal to 9.2K times 6, right? This is equal to 9.4, I'm sorry, 9.4 10 to the 3 times 6 minus 9 times minus 8.2 times 10 to the 3. That's going to be 130.2K. Right? Now, to find my I1 will be equal to the determinant for I1 over the determinant of the system. And to find my I2 is equal to the determinant I2 over the determinant of the system. Right? So this is equal to 132K over 19.4K. K over K is 1, so 130.2K over 19.4K. That will equal to something else, right? So 132 divided by 19.4, this is equal to 6.8. Something doesn't look right here. This is such a high. Now something is not right here, guys. I'm doing something. I don't know what I did wrong, but I did something wrong here. This a little bit. Just give me 1 second. This should supposed to be milliamps, because we are talking about kilo ohm resistor, and then like this is such a very high voltage. Something I did wrong here, guys. Something I did wrong. I know it's not the equations. Let me see. Let me just go to the equations again. So 1.2, 1.3. This is going to be 9.4 times I1 minus 8.2. 9. Okay, that's good. Now a the terminal of the system is very small for some reason. It's should be way bigger than that. So this is this here. So it's minus 8.2 I1 this is 9 point. Oh, look, I didn't see this resistor here. You see the resistor here? I only took care that was those two here. So I need the resistor here. You see the one here now? What I'm talking about? I didn't take care of R3 here anywhere. So my equation 2 will change. Do you see that? Anyone? Okay. So let's fix this part here, right? So this is going to be plus R3. Right, let's put this red. Plus R3, right? That's going to be here plus 9.1. So this number here will be 18.4, right? 18.4. Eighteen point four, right? So that will change a bunch of stuff here. Erase, right? So this is going to change here to 18.4. 18.4. So this one is 18.4 here too. Okay, so this number is going to change. Now we are different. We won't have totally different numbers. So this number is going to be different. All of this is going to be different, right? Okay. Okay, let's do it again. So it's going to be 9.4, right? Times 18.4 minus 8.2 See, now we're going to milli. Now we're talking about. So that will be 1, 2, 3, 4, 5, 6. So it's going to be 105.72 times 10 to the 6. Right? Now the second one would be 9 times 18.4 9.4 times 10 to the 3 times what? Times 6. It's going to be to 214.8K. That should have been the same thing. I shouldn't have erased it, but let's just redo it again anyway. 9.4 times to the 3 times 6 minus 9 . So it's 30.2, the same thing that was before. So let's do the first one. So the first one is DI, right? Which is equal to 214.8 times 10 to the 3 over 105.72 times 10 to the 6. This is equal to 2.03 milliamps, right? And the second one will be equal to 130.2, I think, equal to 1.23, equal to 1.23 milliamps. And this is I1, this is I2. Any questions? Guys, any questions? Okay. So we're going to take a little break here. And then we're going to come back and do the mesh. Thevenin theorem. So you can take a screenshot of this one. You can just, if you understand everything anyway, you can just start doing exercises. Let's be back in 15 minutes, and then we continue through doing the second part of the class. Okay, guys, we're back. Can you hear me? Okay, let me take quick attendance here. I forgot to take attendance earlier. I have to do this earlier. So I think everyone is here. Copy this one. Okay. Paste. So 15, yes. Okay. So let's go back now to, so we close with mesh analysis. So let's do now a, let's see. Okay, this, what else here? I think chapter 9. Chapter 9, probably chapter 9, yes. Yes. Okay. So we're going to do now is we're going to introduce a Thevenin theorem, right? Which is a theorem very powerful that you use in different scenarios. In this one, we're going to use it for two reasons. And one is take a circuit that you have it's a complex network, for example, that you have resistors which are not in series, not in parallel. They cannot be reduced more than what they are, and you may have several sources on the circuit. So what happened? This circuit that I described can be converted into a simpler circuit, which will be composed just of a voltage source in series with a resistor. And that will be the equivalent of the complicated circuit that I just described. And why will you do this? Well, sometimes you, for this case, what that we're going to do now is you have a circuit. Let's say you have a circuit like the same circuit that we saw before, that we just solved. And you remember that R9, R4, sorry, R3 that I didn't see at the beginning. Let's say that if that resistor change, we have to reanalyze the whole circuit again, the same thing that I did. Just because I forgot that resistor, I have to redo almost the whole analysis again. And let's say that we have a range of resistors that we need to insert in that circuit. And then we need to study the circuit every single time. So what we're going to do is, every time that we change the circuit, we have to do all this analysis that we did, the whole thing again, every single time. We have to do it. Now, if we have a theorem that we transform that circuit into an equivalent of a voltage source in series with a resistor, will be very simple now, because the same resistor now that I was telling you, R3 in this case, that we just saw, we can change it every single time, and we have to just connect it to a simple voltage source in series with a resistor, and that's it. Every single time, Ohm's law, every single time we're gonna solve the circuit with just one iteration of Ohm's law, compared to analyzing all this analysis that we spend more than half an hour doing every time that we change it. So this is when we use, for one example, when we use Thevenin theorem. Also, we use to determine the maximum power that can be transmitted to a load, resistor in this case, right? So this is what we're going to be seeing Thevenin theorem being used for in this class, right? So this is the Thevenin equivalent, as you see here, which is just a series of a voltage source with a resistor. And here, between the point A and B, this point A and point B, this is where the other part of the circuit, like the resistor that I told you, or 3 that I connected before, you can put it here. And then you analyze the circuit again. For example, you see the circuit here? In this circuit to the left, we have this circuit. This is a fairly complicated circuit if you compare to this. But we can convert this circuit, this whole circuit here, into this circuit. And then every time that we change our load, we can calculate our L, the voltage across, whatever we need, without the need to go through analyze this whole complicated circuit if you compare it to this circuit. Right? So there will be a series of steps that you have to do the Thevenin equivalent. If you want it, you can just put it down, step 1, step 2, or you can just screenshot those steps that will be telling you to do. Usually theorems have a series of steps, right? So this is what we're going to be doing, right? First of all, when we talk about the circuit, will be referred to this circuit like this in a shaded area, right? So what we do first, we remove, right, the network where you need to find the Thevenin equivalent. For example, in this circuit here, this is the whole circuit here. So what we do is we isolate this part of the circuit, meaning we remove our L from here and then we just leave the point A and point B open. And we take the circuit here, right? You mark the two terminals that you need across. For example, they mark it here A and B. And that's what you're going to do, right? After you do that, now you have to calculate what? You have to calculate the ETH of voltage of Thevenin and RTH or resistance of Thevenin. That's the main goal, calculate ETH and RTH, right? So in order, this is just a step. I'm gonna explain the step to you here, but this is then you're going through the steps. To RTH, first you set all the sources to 0. I will go through this on the example itself, right? So for example, you need this circuit, right? You will first isolate the circuit, which is this part here, as you see here. Isolate the circuit, and you need the terminal A and B, you remove the load. Forget about the load, right? Then, after you do that, you will what? You will take all the voltage source and you will substitute it, the voltage source, by a short circuit, as you see here. You substitute it by a short circuit. If you had a current source like here, you will substitute a current source by an open circuit instead of a short circuit. You just basically remove this, and then you substitute it by an open circuit to two points in. And the voltage source, you remove it, and then you substitute it by a short circuit, right? This is the step number 3, right? Step number 1, isolate the circuit, as you see here. Step number 2, assign the 2 terminals and remove the load. Step number 3, substitute all the sources. Or you have to set to 0 all the sources. In order to set to 0 all the sources, the voltage source has to be substituted by a short circuit. The current source has to be substituted by an open circuit. You do that. After you do that, now between the point A and point B, you calculate what is your total resistance for that point. In this case, those resistors are in parallel, as you see here. This point is connected here, and this point are connected together here, right? So they are in parallel. And you then calculate what is RTH. In this case, will be 3 in parallel with 6, right? So 3 in parallel with 6. That